So at this point, you have either were joined us for the Zoom meeting, and you did the activity with the Zephorgian alien, or you just watched the video on your own and went through the activity. Either way, you hopefully have gotten the idea that there is a connection between average rate of change and instantaneous rate of change. And in the case of the Zephorgian problem we're doing, had to do with velocity. So we did h of h of 2 plus a little bit minus h of 2 over 2 plus a little bit minus 2. And that, the idea that we talked about, that if you set up an interval that's right around the area that, or the place we want to find the rate of change, in this case we want to find it at 2. So we picked 2 as one of our time value, and then added just a little bit to that to get the other time value. Then we evaluated the height at both time values so that we can get, these are both, the top ones are both positions or height above ground. So when we subtract a height above ground from another height above ground, we get a change in distance. So this is change in distance. And then if this, of course, is just time, so this would be the change in time. So when we compare change in distance to change in time, that's velocity. But because we're looking at an interval, this is the average rate of change, or the average velocity. How do we get from that to the instantaneous rate of change? Well, that's where we put the limit in front. Limit as b approaches 0 of f of h 2 plus b minus h of 2 all over 2 plus b minus 2. Okay, so the average rate of change is we're finding the rate of change, the change in distance over the change in time over an interval. And then the instantaneous rate of change, what we talked about in that video, is that if we take the limit of this average rate of change and let the b approach 0, in other words, let these two x values get closer and closer together, which means the interval is shrinking, then if we can evaluate that limit, it'll give us the actual instantaneous rate of change at 2. So that's what we should have got from those videos, or from the session. Either way, the activity with the Zephorgian throwing the rock. So from that, we discovered we need to understand limits. So this video is mostly about just the basics of limits. So the idea is that I take the limit of x as approaches, let's say 0. Let's just do some function like well, let's just keep it simple, like x squared. Okay, so let's look at what that means graphically speaking. Okay, and how is that different than just f of 0, where f of x equals x squared? Okay, so if I just said what's f of 0, that would be easy. The answer is 0, right? So, and that actually represents a point on the graph. That actually is the point 0, 0. Or I could do what's f of 1, that would be 1, f of 2, that would be 4. So each one of these represent a point on the graph. So let's use a red dot for that. That would be 1, 1, and a blue dot for that. That would be 2 up 1, 2, 3, 4. So these are functional values and their coordinates, right? This is the limit, says that I'm interested in what's happening to the y values, because this is representing the y values, as x approaches 0. So I'm not plugging in 0. I'm not wanting to know what happens when I get there. I'm wanting to know what happens as x gets close to 0. So as I'm coming in this on the x-axis from both sides, I'm getting closer and closer to x equals 0. I'm looking at x squared. This is what x squared looks like, right? I'm looking at x squared, and so I'm kind of mirroring my approach. As I come along the x-axis, I'm looking at what the y is doing. As I come along this x-axis, looking at what the y is doing, and I'm trying to figure out where is the y is headed. Well, in this case, it appears that the y is headed towards 0. So in this case, the functional value and the limit as x approaches 0, the functional value at 0 and the limit as x approaches 0 are the same answer. Okay? Now let's look at one that's a little bit different. Let's say that f of x is one of those really fun piecewise functions. Okay? And let's say if we talk about f of 0 or f of 1 or f of, I don't know, 2. Okay? So f of 0, if you plug in 0, and so this is my f of x right here, this graph. If I plug in 0, I get 0. I can see it right there. So plug in 0 for x, get out 0 for y. If I plug in 1, now when I plug in 1, notice I don't get 1 because there's an open circle there. This is supposed to be closed. I would get 2. And likewise, when I plug in 2, what do I get? I go over 2 up, well, it looks like about, hey, come on. Looks like, well, that was a wavy line. It's supposed to be straight. What I meant to do was that. Okay, it looks like if I plug in 2, it looks like I get 3. Okay, so those are functional values. I'm plugging in x values, getting out y values. Now let's ask a different question, the limit question. What's the limit as x approaches, say, 0 of f of x? Well, again, I'm looking at, I'm coming at 0 from both directions. And so I'm coming down this way and coming up this way. And once again, it looks to me like as x approaches 0, the functional value is also approaching 0. Okay? Now, what happens though when I do the limit of f of x as x approaches 1? Okay? So once again, I'll pick a different color here. I'm coming at 1 from 2 different directions. So I'm approaching 1. X is approaching 1, which means my y value is doing that. If I approach 1 from the other side, y is doing this. And the interesting thing is as I approach x approaches 1 from 2 different sides, the y values are doing 2 different things. You can see that there, right? So because of that, we've created this thing called a left-hand limit and right-hand limit, so we can talk about it. So what we can do is we use this notation to say, okay, I'm going to look at one side at a time. So notice the minus and plus, it looks like I just messed up and put it on the wrong side. No. What happened was, this is x is approaching positive 1, but this means it's approaching 1 from the left side, and this says x approaching positive 1 from the right side. So if we erase that color, can I do that? Oh, I missed. Shoot. I didn't miss that one. Okay, so let's use green for this one. So as x approaches 1 from the negative side, that means I'm coming in from this side, which means I am coming, the y value is doing this. And then let's use pink for this one. So this says let x approach 1 from the positive side. So as I come in towards 1 from the positive side, the y values are doing this. Okay, and so you notice that I have 2 different answers. When I approach 1 from the negative side, it looks like it's getting closer and closer to 1. Now notice this open circle here. it doesn't actually get to 1, but that's not what this is asking. This is asking, what is y doing as x gets close to 1 from the left side? So as I approach 1, as x approaches 1 from the left side, it appears that y is getting closer and closer and closer to 1. Now, does it get there? I don't care. That's not the question. And the answer is no, it doesn't get there. But I don't care, because that's not what this is asking. This is asking, where does it look like it's headed? Likewise, when f of x approaches 1 from the positive side, it's not approaching 1 anymore. It looks like it's getting closer and closer to 2. So the answer to this one would be 2. So notice when I approach from the left, the function's getting closer to 1. When I approach from the right, the function's getting closer to 2. So if I ask this original question that I asked, what's the limit of f of x as x approaches 1 from both sides at the same time, because they don't have a plus or minus on either side, then the answer is does not exist, because these two guys disagree. From the left, it's saying I'm approaching 1. From the right, it's saying I'm approaching 2. No 1, no 2, no 1, no 2. Can't come to agreement. So if I approach 1 from both sides at the same time, the answer is does not exist. Okay? So that's the idea of a limit. Now, there's a lot of different ways to handle limits. What we just did is look at the picture. I often call this the nearsighted approach, because I can evaluate the limit by just looking real close at a graph. You know, if I basically go in and try to zoom in and say, well, it looks like it's getting closer and closer to 2 and closer to 1. So really all I'm doing is looking at the graph and seeing where it is headed. So that's called the nearsighted approach, and often that can be quite handy if it's a clear graph and then you can see where it looks like it's headed. Another technique for dealing with proofs, or with limits, I mean, is just average. There's several different algebra techniques. So there is factoring and canceling. There is rationalizing. And there is simplifying. Complex fractions. So these are just some algebra techniques that you in theory already know. You learned them in pre-cal or algebra 2 or algebra 1 or someplace. And so you know how to factor possibly and cancel. You know how to rationalize it, numerator or denominator. You've done that before with rational functions, irrational functions. And I'm sure you've simplified some complex fractions in your day. So these are all algebra techniques we can do to possibly help us evaluate a limit. And then a third method is we can use a numerical approach. Okay. Nearsighted approach means I'm looking very closely at the graph and just seeing where it looks like it's headed. Algebra approach will show you that in the following video, how to, and actually there's a video on specifically on this one too. There's a video on these 3 algebra techniques that'll help you sort that out more. Then the numerical approach is a little bit more tedious. Basically what we're doing is we're taking, let's say I'm trying to evaluate the limit of f of x as x approaches 1. And let's say that f of x is x plus 1 over x. Okay. So the numerical approach would be really just looking at tables. And so kind of like we did in the Zaforian exercise. If we want to find out what's happening at 1, we actually let's let x approach 0. because that's a problem. We don't know what f of 0 is, right? So at 0 we don't know, it's undefined, because when I plug in 0 in there, I get 1 over 0, which is undefined, right? So I'm trying to find out what's happening as x approaches 0. Okay, so so what we do is go to either side of it and we start closing in. So we might start at I don't know, 0.7, 0.8, 0.9, and go back over here and do oh, those would be, I'm sorry, no, what am I doing? Sorry. I would go negative 0.1, negative 0.2, and negative 0.3. And then I might go 0.1, 0.2, 0.3. So then what I'd have to do is actually start calculating that and say, okay, what is f of negative 0.3? And that would be negative 0.3 plus 1 over negative 0.3. So I would start calculating these values, and then I would do, f of negative 0.2, put that in there, f of negative 0.1, put it in there, and then to do the same thing on the other side, f of 0.1, put it right there, f of 0.2, put it right there, f of 0.3, put it right there. And hopefully I should see some kind of a pattern, like this is getting closer and closer to something, that's getting closer and closer to something. And if I do that, I should be able to figure out where these two values are headed towards, and that would be the numerical approach. So this is kind of like the nearsighted. On the near side, I'm looking at the graph. Here, I'm looking closely at the y values that are produced by plugging in x values. And so you can see that I'm looking at I'm letting the interval get smaller and smaller and smaller. So those are my three types of ways of evaluating limits. Again, there's a rule sheet in the Canvas that talks about the way limits behave, so make sure you pay attention to that. It talks about like the limit of f of x plus g of x as x approaches 1, let's say. So there's basically some rules about how things like this behave. It says that the limit as x approaches 1, x plus. So anyway, there's several rules like this that tell you how limits of functions behave. So notice if I'm taking the limit of two functions added together, I can break that into the limit of the first one and the limit of the second one and just add their results together. That's true of the way limits behave. So that's take a look at the limit rule sheet. It has a list of all the different rules like this one. So make sure you take a look at that. It's in the Canvas right below, or I think either right below or right above this video. And make sure you look those over. They're kind of common sense, but nonetheless you want to look at them, make sure that is common sense to you. All right, well, get excited about these limits. We want to just get really good at evaluating limits, and then we'll tie that back into the calculus world that we're so excited to study.